Okay, welcome back, folks. We're continuing to talk about this crucial process of hypothesis testing. This is really important, really exciting stuff. I got it's so intense, my hair is falling out. I'm doing a little board work over here, so wish me luck on that. You might be watching like the 18th take. This might take a lot. This might hit me in the head a few times. Who knows? So anything can happen. We're going to get real wild here. But seriously, this is a really important part of the course overall because we're developing this hypothesis testing procedure. Again, the rest of the class is going to be essentially just variations on this process. So get this down, review this as many times as you need to, and make sure that you've got this idea of creating these hypotheses pinned down as much as possible before you move on. So remember last time we talked about this process being called null hypothesis significance testing. So again, that idea of a null hypothesis is a little odd, but that's the core of the test. That's what we're going to be talking about today. So again, when we run a null hypothesis significance test, we start with some kind of a hypothesis. A hypothesis is a statement. Really, it's a prediction because we don't know it, but it's a statement about population parameters. Those parameters are almost always going to be population means, the mu's. That statement requires some kind of verification. We're looking to test it, basically, see if it's supported or not. So the example that we started with, let's say Doritos claims that as a population, all of their bags of chips of a certain size have on average 185 grams of chips. Again, that's a statement, that's a claim about a population mean. They're saying the mean is 185 grams. What we'd want to do in a hypothesis test is gather data to see if that was true, and the way that we would formulate that test is by saying that we were comparing their claim about the population mean, 185 grams, to the true population mean, what we would call mu1. So mu1 is the real population mean. The way to actually measure mu1 would be to get every single Doritos bag on Earth and weigh them all and average them together, and that's just not going to happen. So we're going to represent mu1 with a sample of scores and make that comparison. But either way, at the start, we're making a claim about population parameters, and we're asking, has Doritos made an accurate claim or not? So to determine this, we need to start with hypotheses, and that's the core of this null hypothesis significance testing process. All right, are you ready? There are two hypotheses, and only two hypotheses, that are in every single null hypothesis significance test. It's a pretty simple idea once you pin it down. There's only two hypotheses. There's only a few different forms they can take. You can see them kind of glibly summed up here. We'll start with the null hypothesis. The null hypothesis is a really important one. That's what the test is named after. Its symbol is a capital H for hypothesis with a little 0 for null. The null hypothesis is what we believe by default about the populations that we're comparing. By default, we always assume that our predicted relationships don't exist. So the null hypothesis is essentially nothing's happening, nothing's going on here. There is no difference between these populations. If you manipulated an IV, it didn't do anything to the DV. Again, this is what we believe by default. The most common form of null hypothesis is the hypothesis of what's called equality. So you'll notice over here, I've written mu1 3 times and mu2 3 times. What this represents is the only 3 ways that the mean of one population can relate to the mean of another. There's only 3 relationships that can be happening there. The first one is the one that's just mentioned here, the hypothesis of equality. Basically, mu1 equals, oh, that is not a good equal sign. All right, that's up to mediocre. Mu1 equals mu2. There's no difference between the populations. And again, if you manipulated an IV, that means the IV didn't change DV scores at all. So this is the most common form of null hypothesis. In our Doritos example, the null hypothesis is that the actual population mean weighs exactly what they say that it does, 185 grams. And notice we can put in the real number here for what we called mu2 over there, the mean of population 2. So the real average weight of Doritos bags is exactly what they claim it is. Then we can create the remaining possibilities get turned into what's called the alternative hypothesis, or H with a subscript of 1. Notice there are only 2 possibilities left. And they both involve mu1 differing from mu2, just in which direction. Maybe we think mu1 is less than mu2. Maybe we think that Doritos is giving us less chips in the bag than they say that they are. They're taking advantage of us. Or maybe we believe that mu1 is greater than mu2. That in this case, that the true population mean Doritos is giving us more chips than they actually say they are. They're really generous and humble about it, or they're just screwing up. But either way, the population mean of those actual chip bags is higher than what they say it is. Generally, when we have this hypothesis of equality here, the alternative hypothesis is going to have to include both of these. So we're going to wrap those both up together. Those are the only other two things that can happen. Now, the alternative hypothesis is usually what the researcher expects to happen. It does not have to be, but it usually is, and it's usually going to be in this case, in this class. The null hypothesis is whatever possibilities they don't predict will happen. So when we take that alternative hypothesis, when our null is just that the two population means are equal, our alternative is that they are different. So again, we combine these two possibilities together and just say mu1 does not equal mu2. It's just a generic statement that there's no difference there. In the Doritos example, our alternative hypothesis is that the population mean of that weight of chip bags is not 185 grams. Notice that between these two hypotheses, we've covered all three things that can happen. None of those possibilities are in multiple hypotheses. They're not repeated between those hypotheses. They are split up, but between those two hypotheses, we've accounted for the only three things that can happen. The two populations could be equal. Population 1 could be bigger than population 2 on average. Population 1 could be smaller than population 2 on average. Those are the only three things that can happen. So again, it's a little bit confusing with the terminology and how it works, but ultimately you're just taking a handful of possible outcomes and using all of them to make these two hypotheses. So here's the nice thing about that. Because there's only two hypotheses being made, and there's only three possibilities, there's actually only three different patterns that null and alternative hypotheses can take, at least so far. It can always get more complicated in statistics, and it often does. But for right now, there's only three patterns that's going to take. The most common is the one we already talked about, the hypotheses of equality and difference. The null, the two populations are the same. The alternative, they are different. Again, as we noted, this is a generic prediction of difference in our alternative hypothesis. It's not saying in which direction those population means differ. It's just saying they're different from each other. That's all. So this is why it's called a non-directional hypothesis. We use non-directional hypotheses in what are called two-tailed tests. We'll get into more depth on that in the next video. But for now, just keep that term in the back of your mind. Less commonly, we sometimes have what are called directional hypotheses. Here, the researcher only wants to test for one of these directions of differences. They either only want to test for mu1 being less than mu2 or mu1 being greater than mu2. So what happens there is the alternative hypothesis just becomes whichever direction the researcher makes their prediction in, and the null hypothesis is the two possibilities that are now left over. So let's see what this looks like. There's only two forms it can take. Maybe the researcher expects that mu1 is less than mu2. In our Doritos example, that means they're giving us less than 185 grams of chips. The actual population mean is less than what they claim it is. In this case, the alternative hypothesis is the prediction that's being made. Mu1 is less than mu2. Now the null hypothesis accounts for the other two. Mu1 could be equal to mu2, or mu1 could be greater than mu2. Both of those get folded up into that null hypothesis. The alternative is just the specific direction that the researcher predicted those means would differ in. The only other possibility is just when we flip the prediction, we think that mu1 is greater than mu2. The true population mean of Doritos bags is more than 185 grams. And in that case, the alternative is just mu1 is greater than mu2. That's the directional prediction that we actually made. The null hypothesis, mu1 is less than or equal to mu2. So those are the only three patterns that it can take. And to make things even simpler, we are almost always, with just a few exceptions, going to be using these non-directional hypotheses. We'll talk about why a little later on. So you're going to have to learn all of these at this point, but the one that we're actually going to use is these basic hypotheses of equality and difference. All right, this is our first point of emphasis. Unsurprisingly, for how much I've emphasized this, this is very important. Again, usually the alternative hypothesis is what the researcher expects to happen. So this is why it's sometimes called the research hypothesis, because it's the prediction of the researcher. Again, it doesn't have to be, but that is usually a good rule of thumb to follow. That whatever the researcher thinks is going to happen, that gets folded into the alternative hypothesis. So why does the test revolve around the null hypothesis? Why aren't we trying to support what we actually think is happening and instead the test goes around the opposite of that, the opposite of what we expect is happening, that null hypothesis. Here's the reason why. It's much easier, and this gets into deep philosophy of science stuff, but just take it at my word for right now. It's much easier scientifically to falsify statements, to find enough evidence to refute statements or predictions than it is to verify them. In other words, it's much easier to find evidence that contradicts or tears down a prediction than it is to find evidence that supports or confirms a prediction. This is baked into the heart of this test, but long story short, for our purposes, it means that instead of trying to verify or support our own prediction, the alternative hypothesis, we try to falsify or refute or reject the null hypothesis, the opposite of what we're predicting, the other possibilities. So we try to build support for what we actually predict by showing that the other alternatives, the other possibilities, are very, very unlikely to be true. So we find that the opposite of our hypothesis is unlikely. It's a little bit mind-bendy, but again, it revolves around that basic idea that it's easier to falsify statements than to verify them. So we find that all the remaining possibilities other than what we predict are just very unlikely to be true. So that's how the null hypothesis works. The whole test revolves around that null, and essentially whether or not the data we see in a sample provides enough support based on probability levels that we'll get into in a bit to either reject the null, to say we falsified that null, that's almost certainly not true, or to fail to reject it. Failing to reject it just means our results were inconclusive. We consider the null to be true by default. We only get rid of it or reject it if there's a compelling enough set of evidence that we feel confident in doing so. Again, probability is what determines that confidence. But everything revolves around the null hypothesis. You make a decision at the end of the null. The decision goes only one of two ways. You either reject the null or not. Usually as researchers, we want to reject the null because it means the alternative hypothesis is much more likely to be true. So again, just a recap of the last little bit of that point of emphasis. The entire thing revolves around the null hypothesis. There's only two things that can happen at the end. There's no nuance here. There's no real gray area. There's only two things that happen at the end. So one of the few blessedly simple things about this process. One of two things will happen at the end of every single hypothesis test this semester. Either you're going to find strong enough evidence that you believe the null hypothesis has been falsified, and you'll choose to reject it. We're going to learn how we do that in the next couple of videos. Or the evidence isn't compelling enough, it doesn't make it past whatever threshold you've set, and so you do not reject the null hypothesis. Some people will say you retain the null. Retain is a pretty good way of thinking of it, because the null hypothesis, we believe it's true unless we see really compelling evidence otherwise. So retaining it just means we haven't changed our minds. So again, no matter what decision you make, you could always be wrong. This is tough for people to get their heads around, because in math classes or classes that involve math, usually you think, okay, if you do everything right, calculation-wise, you're going to get the objectively right answer. Well, this is not a math class. This is a class that uses math, and here, because we're making conclusions about populations based on samples, we always could wind up with the wrong answer, even if you do everything right. There's always uncertainty there. You are guaranteed to make the wrong decision sometimes, even if all of your data are accurate. So that's going to happen just due to pure chance. Again, it's tougher sometimes for students to wrap their heads around, but there's always the possibility, no matter what decision we make, that we could be wrong, because we know that over a big enough set of decisions, we will be wrong some of the time. It is literally inevitable. So here's roughly how we're going to do that, and then we're going to learn the nuts and bolts as we go on. We create a sampling distribution, remember those, for whatever our sample size is. We place the sample mean on that sampling distribution. We find the probability that we'd see a sample mean with that relative standing if the null hypothesis was true. So we're weaving a lot of concepts together. Even if you don't quite get what that means, you hopefully can recognize a lot of the different terms that we've covered. So we compare the mean of a sample, which represents population 1, to the mean of a population, or oftentimes another sample mean, and we calculate that probability. How likely is it we'd see a difference like this purely due to chance if the null was true? One thing to keep in mind, the more people you measure, the more the standard error gets smaller and smaller. We'll see that when we start calculating these actual hypothesis tests. All right, that's the end for now. Next up, we are going to talk about how we make those decisions about whether to reject the null or not. See you there.